All right, let's start looking at 6.2. We're going to look at trigonometric form of complex numbers. And what happens here is some people will call it a polar form, which is technically not true. So I believe the author has done this, and I'm going to kind of distinguish the difference between the two. And we're just going to call it trigonometric form of a complex number. So we're going to have our traditional a plus bi. Anytime it's in this form, that's our standard form, or some people call it rectangular form because it associates with the xy coordinate plane, your rectangular x and y coordinate plane. So some people will change the a plus bi to x plus yi. It's the same thing. No, it's nothing different. So we're going to let the a, which is our real number, they're going to represent the x-axis. So we're going to have what we call a real axis. And then our bi, or our yi, if you will, anything with an I, that term is going to be your imaginary axis. So what we're going to be able to do is graph your complex number in an xy coordinate plane. Oh, I'm sorry, real axis, imaginary axis. So if we do that, then all of our trigonometry rules come back to play when we did our coordinate geometry. So here again, x plus yi, same as a plus bi. If you want to call this the a-axis, this is the b-axis, that's all fine and dandy. But again, notation-wise, very important. Remember, you have your component form. So again, we're going to take our imaginary number, AB or X, ABI or X plus YI, XY, or AB in component form tells us the tip of our position vector, where we can write it in component form. And there is my vector. Now remember, our vector notation also had the unit vectors I and j. So it's important to understand that you see that little scripted I, that's imaginary. A bold-faced I is the vector. Do not get the two confused. All right? So looking at graphing complex numbers, -3 minus 5i. In component form, that's -3 comma -5. So starting at the origin, we'll go 3 to the left, we'll go down 5. There's the point. That's the tip or the terminal point of my vector. And now I've just graphed this complex number in the xy coordinate plane, and I'll be able to do trig functions with it. Graph 6i. Okay, so technically there's no real number, so that's a 0. So in component form, this is 0 comma 6. So start at the origin, 0. We'll go up 6. There's my vector. And now again, we have an imaginary number graphed in our xy coordinate plane, so we can apply trigonometry to it. Now, here comes the goof ups. Trig / polar form of complex number, says this author. I say, no. This is trig form. Z is called the modulus. It's like your magnitude. This is equal to r times cosine theta plus I sine theta. That was our trig form before, except there was no I here where we use this to represent our vectors. So, but because we are now graphing our complex numbers in the xy coordinate plane, we can use that same trigonometric notation. We just have to remember to multiply the sine of theta by an I. That's our BI part. Now, what irritates me is that polar form is technically a point. It's r comma theta. All right, when we know that this r and this r, well, they might represent the same thing. Well, sort of. This r is the length of your vector. This r is the radius on the polar axis graph. And theta is going to be the rotation of that point on the radius. So we know r is the same as our magnitude. We can also distribute in the r if you like. And we can also see this in component form. Don't worry, we're going to shorthand this notation in just a few minutes. Now, what bothers me is they're going to say graph this complex number that's in trig form. Okay, wait a minute. This is in rectangular form. So when they say they want to graph this in polar form, they mean find the r value, which has to be positive, find the theta, okay, 135 degrees, and plot this, but it's a point in polar form. So that's like saying, okay, here's your polar graph, kind of like a bunch of unit circles here. Okay, there's the unit circle with radius 1, but then there's radius 2, 3, 4, 5. Oh, that's where I want 5. And then you rotate 135 degrees, and when you get to that ring and that 135 degree line, that's where I'm going to plot my point. Now, I get it in the xy coordinate plane, yes, if I position vector, initial point, terminal point, that would be my vector. But polar form is a point. It is not a vector. So I did not like this terminology, so I'm going to stick to trigonometric form. So, your turn. Plot the point in polar form for this, if you will, this trigonometric form of a complex number. So, radius 9, theta 330 degrees. All right, go out to the circle of 9, and we're going to go 330 degrees all the way around. It's getting me dizzy. And plot a point. Or you could have started at 9, and we could have went in a negative 30 degrees. See, that's the difference that I think that is not being talked about here by this author. Polar form can have a negative r. I don't know why they didn't draw it in here. This can be negative 1, negative 2, negative 3, negative 4, negative 5, 6, 7, 8, 9, out to 10. You can start with a negative r value in this direction and then count in a positive angle or a negative angle. So again, technically, this point here, I could have said negative 9 and 150 degrees. And that would take me to the same point. I could say 9 and theta is negative 30 degrees. All working. Different ways to write the same point. And I don't think the author distinguished between this very well. All right, so here in example 3, we have some complex numbers that have been graphed in a rectangular graph. We want to write its rectangular form in a plus bi or x plus yi, and we also want to write the trigonometric form, not polar form, trigonometric form. Okay, so that means find the terminal point because we want to treat this like a vector. I'm at a negative 11, comma 0. Okay, so that's the real number, real axis, x-axis, imaginary axis, imaginary number. So this would be a negative 11 plus 0i. Okay, again, remember those directions that if it says they want it written in a plus bi form, if one part of that is 0, you got to put a 0i in there. Now, trig form, okay, well, wait a minute. What's my r? It's not a negative 11. The distance of this vector is positive. It's an 11. And I have my vector direction angle at 180 degrees. Okay, so trig form, 11, not a negative 11, a positive 11, cosine 180 degrees plus I sine 180 degrees. In trig form, this r is always positive. Remember, we did the magnitude, the square root of x squared plus y squared. Everything becomes positive. All right, second graph. Find the terminal point. Let's see, 2 away from both top and bottom. 18, 18. There it is. Okay, so let's see. I'm going to turn this into a right triangle right away. 18, 18 theta. Here's my r. So I can have this when I get ready for the trig form. But my rectangular form is 18 for the real number, 18 for the imaginary number, so that's 18i, the vertical component. Now, if you don't see it, that's fine. Use your r value, 18 squared plus 18 squared. Simplified radical, well, that would be 2 times 18 squared, so that's 18 comes out in front with the square root of 2, that's your r. Then if you use your theta, inverse tangent of y over x, well, that's a 1, that's 45 degrees, so there's a 45-degree reference angle there. So now I'm ready to put this in trigonometric form. 18 square root of 2 times the cosine of 45 degrees plus I sine of 45 degrees. So, to look all this over, here's everything we need. The relationship between x, y, or a and b, r and theta, is as follows. X is always r times cosine theta. Y is r times sine theta. R, the square root of x squared plus y squared. Hint, hint, always positive. Tangent theta is y over x, but again, x can't be equal to 0 because then that would be undefined. Or, if you prefer, just take the inverse tangent of y over x. And if you want to remember that, that works too. So the magnitude or the modulus of z equals x plus yi is the distance from the origin to the point xy. That's the magnitude, the length. Now, we have a shortcut notation for trig form, and I'm so happy to finally talk about it. Instead of saying r times cosine theta plus I sine theta, we're going to shorthand this. Important letters are the r, the c for cosine, the I for the imaginary number, the s for sine, and our theta, which is the same for both. So why do we write it twice when we can write it once? So I'm going to use this a lot.